Hello, welcome back to AC Circuit Analysis. We're doing delta Y circuit problems. This is problem number 3, and this is going to be what I really consider to be our first really full-blown problem that has a delta source and a Y load. So what we have again is a wall of text that we need to decipher, but the process is going to be the same. We're going to decipher what we have in this problem. We're going to draw a picture, and then we're going to step-by-step inch our way forward through it. Now what you need to realize is that since now we have already done all of the Y problems in the past, and we've introduced and done some kind of simpler problems with the delta source, right? Now we're putting it all together. So some of this problem is going to be dealing with the delta source. Some of it's going to be dealing with the load end of the problem. So the stuff that you've learned in the past is all going to be brought to bear because we're going to be doing things like voltage conversions in the way that we've done them in past problems. We're also going to be doing current conversions as we've been doing them here in the delta sources. I guess what I'm trying to say is that now we're to the point where we're putting pieces together from different parts of the course. So some of the parts of this problem will look like things we've done before because they are things that we've done before, while we'll have some new pieces in the delta source part of things that we've been talking about here. So enough talking, let's get to it. We have a balanced negative sequence circuit. It's a delta source, and it has an impedance of 0.018 plus J 0.162 ohms per phase. So this is all talking about the source. So the delta source is a delta balanced negative sequence source, and the source impedance is what's given by this in each leg of that delta. And then it says at no load, we'll talk about that in a second, at no load, the terminal voltage of the source is 600 volts. Okay, so that's a piece of information. Then we talk about the line impedance that this source is connected to. It has an impedance given here, 0.074 plus J 0.296 ohms per phase. So that's talking about the line. And then that line is connected to a Y load. So you see it's a delta source and a Y load. And the Y load has an impedance as given by this. Notice the line impedance is an inductive impedance because we have the positive J. But the Y load has actually a capacitive impedance because we have minus sign. So we have a real and imaginary part, so resistive and capacitive part of the load. So we have 5 things we want to do. The first thing we want to do is what we always want to do anyway, usually, and that's to draw a single phase equivalent circuit, but it says that it wants you to use VAB prime as the reference. I'm going to get back into what that means a little bit more in a second, but basically we're drawing a single phase equivalent circuit, and when you're using something as a reference, it means that you want to use that as your 0-degree phase. When you see some problem that says use this as a reference, it just means it's code for take that to be 0 degrees phase, and everything else, every other phase angle in the circuit is just going to be relative to that reference, which is 0 degrees. Part B, after we've written the single phase equivalent circuit down, we're going to find the magnitude of the line voltage at the load. So we have like VAB, for instance, but we're only asked to find the magnitude, and we're asked to find that magnitude of that line-to-line voltage at the load. Next, we're going to find the 3 line currents. It's not too big of a surprise, AA, BB, and CC. So once we find one, we'll find the other 2 by adding and subtracting 120. And then we'll find the phase currents in the source. Phase currents, remember there's a triangle. The delta source is a physical triangle, right? So we want to find the phase currents, which are circulating, I shouldn't say circulating, but they're present in these 3 legs of that triangle. And we have them labeled here. I, BA, CB, and AC. And if you remember, we talked about this in the last section and also previously. In a delta source, the subscripts here for the currents that are circulating around that triangle are flipped around. So usually, like for a load, it's AB, BC, CA, goes like the alphabet. But on the source side of the circuit, we flip these subscripts around. So for the A phase, instead of AB, we're trying to find BA. Instead of BC, we find CB. And instead of CA, we find AC. So basically, we're just flipping the subscripts around. And that comes about because this is a source, so the current has to be leaving the power supplies. And we'll draw a picture, and you'll see in a second. But that's why these subscripts are backwards from what you might expect there. And then the last thing is to find the magnitude of the line voltage at the source terminals, the magnitude of the line voltage at the source terminals. All right, so the first thing we want to do is draw this single phase equivalent circuit. And you're always going to start by drawing them basically the same sort of way. So you have to draw a triangle, and in each leg of this triangle, we're going to have a resistive part and an inductive part, and then we're going to have some kind of source in each leg of the triangle. So let me quickly draw this guy. So I'll have an inductor here, resistor here, we'll have some kind of source here, here we'll have some source here, then we'll have resistive part, inductive part, and then we'll kind of close our triangle off like this. Okay, and then what we will do is we'll have plus minus here, plus minus here, and then plus minus here, and you can see minus to plus, minus to plus, minus to plus. That's how we're drawing things here. And then what we have is at the top of this guy, you know what, let me switch colors to this. At the top of this triangle, this is terminal A. And for sources, remember we label the triangle slightly different. This is terminal C, and then this is going to be terminal B. And then what's basically going to happen is you have one of your three phases of your line. It goes this way, and then it looks like I put my B in the wrong place, so I'll kind of grab it out this way, and then we go down here. This will be the third phase. So we have A, B, and C. So we have a black box of a source, three phases. Then we have a line impedance and a load impedance down there. I'm not going to draw those right now. We're going to end up drawing the line impedance and the load impedance when we actually do the single phase equivalent circuit. Right now, I'm not drawing the single phase equivalent circuit. I'm actually drawing the delta source, because for some reason, if I don't draw the actual delta source triangle, I end up getting confused with what I'm trying to solve for. So I'm just going to do that exactly as I do it when I solve my own problems. Now, in the problem statement, it tells us we have a negative sequence delta source, and here is the source impedance. So it's 0.018 and J 0.162. So 0.018 ohms for the real part, J 0.162 ohms for the inductive part. Now, I'm not going to write it down for this and for this because I don't want to crowd the diagram. But this inductance, these inductances are all the same, and these resistors, of course, are all the same because this is a balanced circuit. Now, the other thing I want to write down is, so this is the, let's go here. Between A and B, this is the A phase, right? But just for completeness, since we have a source here, I'm going to go ahead and mark this down as A prime. So the, I should say B prime, actually. Whoops. So between, let me take this whole thing away. Sorry about that. So B prime. So between A and B is the entire source, including its internal impedance, but between A and B prime is just simply the voltage source itself. You don't always have to write these things down. I'm just doing it for completeness mostly. I don't even know if we actually use these particular labelings in this drawing here, in this particular problem here. All right, and the next thing we want to do, you don't have to, but again, I like to do it, is I want to draw the current circulating around in this triangle. You know, I talk about the word circulating like they're going in a circle, but that's not what I mean. I just mean the currents in each leg of the triangle. They're different sinusoids and they're out of phase with one another. So normally between A and B, it would be IAB, but in a source, we actually go backwards. So the current's coming out of the source. So this is actually IBA, flowing from B up to A, so everything's backwards. And then we have the current going from here to here, again, coming out of this source, so it's going to be going from C to B. Normally, you'd flip it around and say it was BC, but we flip it around and go that way. And then we have a current going down here, again, coming out of this source, we say IAC. So again, for the A phase, usually it's AB, BC, CA, but because it's a source and we flipped around the labeling of things, and the current goes in the other way, we actually say instead of AB, it's BA, instead of BC, it's CB, and instead of CA, it's AC. So that's how we write them down. That's the main reason I write the triangle down, so that I don't have to think about which way the currents are flowing and what they're labeled. I have it all there ready to go. And then, of course, connected to this is our three-phase line, each with the same impedance, and then we're connected not to a delta load, we're connected to a Y load. I'm not going to draw that now because it's not necessary. We'll do it when we do the single-phase equivalent circuit. Now, actually, I'm glad I did put these primes here because we go back to our problem statement. We have a delta source. Here's the impedance. And then here we go. It says at no load, the terminal voltage of the source is 600 volts. The terminal voltage of the source is 600 volts. So what does it mean at no load? At no load. Think about that for a second, at no load. What that means, we have a power supply. It's a delta source. It's got three phases in a box here. The only thing coming out of that box is three wires because the power supply is like hidden away in a closet somewhere. I have the three lines coming out of the box here. And inside this thing is a three-phase source, delta source. Okay? What we mean by no load is if I connect a voltmeter up to the terminals, in fact, it tells us which ones, at no load, the terminal voltage of the source is 600 volts. So let's say between A and B, I measure the voltage between A and B. It's saying at no load, meaning current is not actually flowing out of the power supply. In other words, if I remember, voltmeters have an infinite resistance. They're designed that way. They're designed to measure the voltage, but not to actually allow any current or very minuscule amounts of current to flow out of the circuit. That's the whole point. The ideal voltmeter has an infinite resistance. So if I connect a voltmeter here, I measure the voltage, but no current actually circulates through the voltmeter because I've designed it in such a way to not disturb the circuit. If a voltmeter had a low resistance, then as soon as I connect it, a bunch of current flows out of here, and then I've changed the circuit because now current's actually leaving the circuit and it changes, potentially the voltage drops inside. What I want to do is I want to measure that voltage but not disturb the circuit. So real voltmeters have a designed impedance to be very high. So when it says here at no load, what you're really saying when you translate the language is I hook a voltmeter up and I measure that voltage. It has an infinite resistance of the voltmeter, which means I'm not loading the circuit down with anything. No current's flowing out of the circuit at no load. That's what that means. That voltage drop is 600 volts, right? So really what you're telling, it's not telling you this in plain language, but what's really happening here is that VAB prime, for instance, or just the magnitude of VA prime, is 600 volts. Now, the problem statement could have just said, hey, a balanced source has la 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 la, and it could have said, hey, VAB prime, the magnitude of it is 600 volts. But that would be too easy, right? Because then you draw the triangle, you know where A and B prime is, it's basically the voltage of the source without any current flowing anywhere else, then you would know that that was 600 volts. But you have to read between the lines. It's kind of part of learning things, right? So when you say that we have a source with no load, the terminal voltage is 600 volts. What you're saying is between A and B is 600 volts. That's what you're saying, between A and B is 600 volts when you don't load it down. But what you're also saying there is you then know that the voltage internally here is actually 600 volts, because if there's no current flowing through this leg, if you haven't connected anything anywhere, there's no current in this leg. If there's no current here, then the full 600 volts must be across this guy, because there's no current going through here. There's no drop across this at all. So if you have 600 here at no load, then it must be true that this internal source is 600 volts. That's actually crucial to what we're trying to do down the road. Okay? That's crucial to what we're trying to do down the road. The other thing it tells us is we're to draw a single-phase equivalent circuit, but we're going to use VAB prime as a reference. VAB prime as a reference. So right here I wrote it as an absolute value, 600 volts. Now I'm going to take that absolute value away, and I'm going to say that, hey, since it told me to use this as a reference, I'm going to say it's 600 at an angle of 0 degrees. Okay? So that's what basically it's telling you. I could have said, hey, the A source, VAB prime, is 600 volts at 0 degree phase angle. Use it as your reference, and then you would know exactly because you'd have a number. But when you say things like at no load, this is what happens, then you have to think about it a little bit and say, what does that mean? It means AB is 600. There's no current here because it's not loaded down. That means this must be 600. And because it's my reference, it's 600 at 0 degrees. That's important. Okay. So the next thing we're going to do is we're going to do our single phase equivalent circuit. So we have a delta source. We have to convert it to a Y source. So we know the impedance here of each leg. It's 0.018 and it's 0.162. So we're going to do and say if we change that to an equivalent Y source, it's 0.018. Plus J 0.162. We're going to take that and divide by 3. Okay, so then I'm going to say that the equivalent Y impedance, if we change that to a Y source, is 0.006 plus J 0.054 ohms per phase for the Y configuration. So I'm going to keep that in my back pocket because I'm going to use that for my single phase equivalent circuit. So part of converting this to a Y source is to take the impedance and find the equivalent impedance for the Y source. The other thing I have to do is I have to take this internal voltage source and I have to convert it to some other equivalent voltage source if we were to build this as an equivalent Y source. So now that we know that this is 600 at an angle of 0, then we can apply our equation. The source voltage when I transform to a Y is going to be equal to 1 over the square root of 3 times the voltage of the source in its delta configuration, and then it's going to be shifted by either minus or plus 30 degrees. Now go back to my problem statement and I remember, hey, this is a negative sequence problem. So top sign is positive sequence, negative sign, or the bottom sign is for negative phase sequence, so it's really going to be shifted by positive 30 degrees. So if I want to convert this delta source to an equivalent Y source, it's going to be 1 over square root of 3. And the voltage source over here for the delta configuration, we said is 600 at an angle of 0 degrees. Now you see why it's so important to understand and read the problem statement to understand that. And then it's 1 at an angle of 30 degrees. We're shifting. So the voltage source, if it were a Y configuration, is going to be 346.41 at an angle of 30 degrees. Okay? So basically you multiply this stuff and you add 30 degrees there. So now you see why it's so important to read the problem and draw this picture first, because it just tells you the terminal voltage of the source at no load is 600 volts, and you have to know by process of inference that if this is 600 volts and there's no current here, if it's not loaded, then this is 600 volts. And because it's a reference at 600 at 0, because I'm going to use this voltage source to come plop into this equation to convert it to an equivalent Y source. All delta sources must be converted to an equivalent Y source in order to write your single-phase equivalent circuit. So that's what we're going to do next. We're going to use these two pieces of information to write our single-phase equivalent circuit. All right, so we have... Let's see here, how much space do I need for the other part? Yeah. Okay, so let's go over here and say, well, for this guy, we're going to have a voltage source, right? We always have a voltage source. And then we have some source impedance associated with the source. Then we have our A terminal. Then we have some line impedance. Then we have the capital A terminal over by the load. And then for the load, we have some load impedance. And then in this particular case, it's a capacitive portion of the load there. So that's basically what we have here. Now let's go through every little piece of this circuit and write down everything that we know. So the source, right, for the equivalent Y source, we just found what it is. It's 346.41 at an angle of 30 degrees. Okay, that's the voltage source. Right? Now notice in the original problem it says we use, let's see here, at no load we do this guy here and then we use this as a reference. We are using this as a reference. VAB prime is the reference. But when we convert that to the equivalent Y circuit, of course it's shifted, so this is the voltage source we use for the equivalent Y circuit. So that's what we're going to do for our single phase equivalent circuit. Then we look at the transformed source impedance. We don't look at the original problem statement source impedance. We have transformed that using this equation. So what we're going to have is 0.006 ohms and J 0.054 ohms. All right? And then we look at the line. We have a resistor and an inductor. We go back to our problem statement and we scan down here. The line impedance is 0.074 plus J 0.296. So 0.074 ohms, J 0.296 ohms. This is the resistive part, this is the inductive part right there. And then we go look at our load. Remember, when we do a single-phase equivalent circuit, in order to put it into the circuit, it has to be in a Y configuration. For the source, which was originally delta, we transformed it to Y. But in this problem, it tells you right here that the Y load has the impedance of blah, blah, blah. So the load is already a Y. So we don't have to transform anything, it's already in a Y. And notice that it has a negative sign here. So it has a capacitive component and a resistive component, 7.92, and then negative J 6.35. So we say 7.92 ohms, and then negative J 6.35 ohms. This is our single-phase equivalent circuit. The only thing I want to add is that over here, of course, on the Y side, you have three phases, and they all come together at a common point. We call this the neutral terminal, so we call that capital N. Now on the source side, we actually say we have a neutral terminal here, lowercase n, because this is a transformed source. It's behaving like a Y source, so if we built it, we have to build three different phases, and they would all come together at this point. But this lowercase n here, it doesn't really exist in the original triangle. There is no common terminal, there is no neutral terminal here. But when we take this and we transform it into the Y domain, for lack of a better word, then we pretend, I mean, effectively, if you were to build it this way, it would have a neutral terminal if you had built all three phases. So we label it lowercase n. So that's about all I have on my diagram, except for one thing. I want to say that here, if this is the source, the current's going to be circulating this way. So I'm going to go ahead and put up here an arrow I, little a, big A. Current coming out, circulating around our single-phase equivalent circuit. So we go back to our problem statement and we have completed A. Draw a single phase equivalent circuit using VAB prime as a reference. That's what it is for the A phase. Then, part B, find the magnitude of the line voltage at the load. The line voltage at the load. So we have to look, at this point, you start transitioning yourself from using this cumbersome diagram over here with the actual delta source triangle to using the single phase equivalent circuit as a tool. And so we ask ourselves, how are we going to find the magnitude of the line voltage at the load? First of all, what is a line voltage? It is AB, so VAB, V is not drawn here because it's a single phase, but VAB or VBC or VCA. Those are all line-to-line voltages, but we're just going to find it for the A phase because ultimately all we want to find is the magnitude. So we're just going to find the line voltage for the A phase. We'll take the magnitude of it and circle that as our answer. So how do we find the line-to-line voltage? Well, step number one would be, we know this voltage source, we know every impedance in the circuit, so we can use Ohm's law and calculate this line current AA. That's almost always what you do first. Once we know AA, we can find the voltage drop VAN. In fact, I think I'll go ahead and draw it there. Plus, minus, I'll kind of draw a little arc here, VAN. The voltage drop between A and N would be measured from here to here. It's basically the voltage drop across that part of the load. But this is not a line-to-line voltage, that's a line-to-neutral voltage, remember? And so when voltages are different, in this case in a Y load, a line-to-line, line-to-neutral voltage is different, then we have to use the voltage shifting formula. So step one, we find the current circulating. Step two, we find VAN using Ohm's law. Step three, we shift VAN using our voltage shift formula to find VAB. And that's what we're trying to find for this problem. It sounds complicated, but it's really pretty trivial math. I mean, it's not like you're doing like a three-dimensional calculus integration or something. I mean, it's just a bunch of Ohm's law in the complex phasor domain. So the first thing you want to find out is what I'll do is I'll find AA on this board, and then we'll go to the next board to finish the problem. IAA, what's it going to equal? It's going to be, you know what, I'm going to need a little more space. So let me go ahead and shift myself over here a little bit. I, little a, big A. What is it? It's the voltage source divided by all of this stuff added together. So you say 346.41 at an angle of 30 degrees. And we draw a big old division bar. We have this impedance, 0.006 plus J 0.054, plus this impedance, 0.074 plus J 0.296. And then we have this last one plus 7.92 minus J 6.35. Barely fit. So you get your calculator out, you add up all these complex numbers in the rectangular side, format on the bottom, and then you have a polar complex number. You divide the guys here, and what you will get is the current circulating in the A phase through the line is, let me just double check I have everything correct here. You're going to have 34.64 at an angle of 66.87. And that's amps RMS, of course. So I'm not actually going to circle that because that's not a final answer. It's the very important answer, though. It's actually the lion's share of the problem. It's the current circulating through the A phase of the line, which, of course, then goes straight into the A phase of the load. So now we want to find VAN. So what's it going to be? It's going to be the current here times this impedance, right? So this current, which we just found, times this. So let's go ahead and find that next. And what we're going to have here is V capital A capital N is going to be the current times the impedance. We just found that current. It's 34.64 at an angle of 66.87 times 7.92 minus J 6.35. So this is the current circulating into the load, and this is the load impedance for the A phase. So VAN, when you just do a straight multiplication, you get 351.64 at an angle 28.15. Okay? And that's, of course, volts RMS. So that's VAN. That's the voltage across this part of the load. Now you have to take this because this is not a line-to-line voltage. This is a line-to-neutral voltage. Our problem statement didn't ask for that. Problem said find the magnitude of the line, we call it the line voltage, but you now know that that means line-to-line voltage. So since line-to-line and line-to-neutral are different, we have to shift between them. which we've been doing for every one of these problems in the past when it's a Y load like this. So we're going to shift. And the shifting formula is VAB, that's the line voltage, is equal to the square root of 3 times VAN, which is the phase voltage. And you shift by either plus or minus 30 degrees. But we go back to our problem statement, and it says it's a negative phase sequence problem. You choose this for positive phase sequence, and you choose this for negative phase sequence. So we just erase that one, and we're shifting by negative 30 degrees. So now we just plug in what we have here. So we say, save a little space here. It'll be, VAB will be square root of 3 times VAN, we're going to write it down here, 351.64, angle 28.15, 28.15, sorry about that. And then we're going to shift it by negative 30 by multiplying by a phase angle like this. So you multiply these magnitudes and you add these phase angles. This is 28.15. Sorry, that's a little hard to read. Let me just double check myself, make sure I'm caught up. Then VAB is going to be equal to 609.06 at an angle negative 1.85. Now I was able to find the complete line-to-line voltage, VAB, including its phase angle, because I had all the information on the problem, but actually it just says find the magnitude of VAB, right? Which you just take the magnitude right off the front, 609.06 volts RMS. And that's what you circle for your answer. Now really, when you get to this step and you're doing the shifting, you know, I figured out the phase angle and all this stuff and I wrote all this down. Really, since you know you're finding the magnitude, you can throw away the phase at this point because you're just going to add them and then throw it away anyway. You could just take this times the square root of 3, which gives you this, which gives you this. So this is the magnitude of the line voltage at the load, which is exactly what we were asked to find. All right? Now, that's what part B. Part C, find the 3 line currents. AA, BB, and CC. Now, as part of the process of solving this problem, we actually found the first line current, AA. So that's actually given. How do we find the other 2? You do it just like any 3-phase problem. You know the phase sequence. So you take your AA, your A phase current, and you either add or subtract 120 from that to get the other 2 phases. Now, in order to prevent yourself from, getting a bad grade for no reason, I always draw a diagram. So the A phase is here at 0 degrees, and since it's a negative phase sequence, that means that you have C here, and that means you have the B phase here. ACB, that's a negative phase sequence, right? And so that means to go from A to C, you subtract 120, and that means to go from A to B, you add 120, just so you don't confuse yourself. So the way that you write this down is you say that IAA is equal to, I'm just going to write it down, 34.64 angle 66.87. Okay, this is the A phase. Now to get the B phase, what do you do? Or the C phase, or whatever. You can go in whatever order you want. Let's go in the B phase. Little b, big B. 34.64 angle 66.87. Now to get the B phase, I have to add 120 degrees to that phase angle. So BB is 34.64, and when I add these guys together, I get 186.87 degrees. That's that part right there. And then the last part is I, little c, big C, same magnitude, 34.64, angle 66.87. Now to get the C phase, you start A phase and you go backwards by 120. So CC, 34.64 angle. Now I subtract, and I'm getting negative 53.13 for the C phase. Of course, these are all amps, RMS amps, so I can write that down. So that's it. And, you kind of find the A phase line current as part of the problem statement. You just find the other 2 because you know that these are a balanced 3-phase set. Now we have to be a little careful as we do part D and part E, because here's where things can get a tiny bit confusing if you're not careful. Part D says, find the phase currents in the source. Now I've labeled them for you, but ultimately you don't really need me to label them because once you draw your own picture, you know what they are. The phase currents means those are the currents going through each phase. So this is what I've labeled on the diagram. You have IBA going through this source, you have IAC, and you have ICB. Subscript-wise, it's the exact reverse of how you would label it on the load side. So usually it's AB, BC, CA. We flip them around because it's the source. Okay. So the trick to this guy is basically what you want to do is you want to find out what one of these currents is. So we're going to focus on this one. We're going to figure out what this guy is, BA, this current. Once we know what one of them is, just like all of these balanced three-phase currents, you just find the other two by adding and subtracting 120, just like we did a second ago. So the entire part of this problem is just going to revolve around figuring out what this current is. So how do we find that? All right, the way that we're going to do that is the following. Remember, we have a shifting formula that's useful when we know the line current and we want to find the phase current. Remember, when we have a voltage formula when the phase voltage and the line voltage is different, and we just use that. And we have another formula when the line current is different from the phase current, which is what we have here. We know the line currents, we know all three of them, right? So in this case, we'll focus on AA. That's the current coming out of here, right, going through this line, and we're going to just shift it using a shifting formula, which is going to give us the line current BA coming through this leg of the triangle here. So what is that shifting formula? We've been using it, you know, forever. Maybe I want to do it here, actually. Yeah, just because I'm running out of space. So let me go here. What is that guy here? Well, we know that the line current, AA, is equal to the square root of 3 times the phase current, BA. Remember, it's AB but flipped around, right? And then you shift that current by either negative or positive 30. This is the exact same current shifting formula we've been using for delta loads and delta sources. Positive phase sequence, negative phase sequence, so we're going to erase this guy. We're going to use the positive sign in our equation. Okay? Now, we know the line current. We actually found it. It's right here. So we're going to stick this guy in here, and then we're going to divide by this and divide by this. So if we're going to solve this equation for IBA, which is that phase current going through that triangle, it's going to be 1 over the square root of 3 times IAA, the line current. And then when we divide by the phase guy here, this positive 30 turns into a negative 30. We've done that enough where you should understand that by now. So then what we're going to do is we'll plug everything in. 1 over the square root of 3. And then this line current is here, 34.64, angle 66.87. So it's 34.64, angle 66.87. All right, and then we have negative 30 degrees, like this. Okay, so then you take the magnitude, you divide it by the square root of 3, you take this phase angle, and you're going to subtract 30 from it, essentially, and what you're going to get, we'll do it in red, IBA, whoops, little a, because we're on the source side of the circuit. Let me just double check, I've got everything in place here. Yeah, you're going to get 20 at an angle of 36.87. This is one of the 3 phase currents. This is amps, RMS. So what you have found is IBA. It's the A phase current for this phase. It's the A current for the A phase, basically. So this is the line current coming out of here. We just shifted it to find this phase current here. Now, how do we find the other parts of the triangle? This is the A phase. To find B and the C phase, we just have to add and subtract 120. So here's where, again, it gets a little tricky. But what we know is this one. This is what we just found. We found the A phase current. So we're going to add 120 to get one of these answers, and we're going to subtract 120 to get the other answer. So the way we do that is, okay, so what we just found, this is how I keep it straight in my head. What we just found, I like to think of it as AB, but we reverse the subscripts to BA. We just found this on the previous board. We just found that. So then I have to ask myself, okay, this guy here is like right here. So then what do I find next? What do I get when I subtract 120 degrees? I get C. So typically I think about this as CA, but we flip around the subscript so it's actually AC. So this is what I'm going to find next. So to find this guy, it's going to be the exact same thing we found for this, 20 at an angle of 36.87. This current is exactly what we just found a second ago, but I'm going to subtract 120 degrees. So IAC is 20 at an angle negative 83.13 degrees. I'm going to circle this guy. So you see now what we have is we have the A phase current. Usually it's called AB, but here it's called BA because we're in the source. This is what it was. Then we subtracted 120 degrees from it. Usually we call that CA, going down to the C phase to get CA. But we flip around the subscripts because we're in a source, and we call it AC. Now the next thing we're going to do is we're going to take that A current, we're going to add 120 to get what we call the B phase. Usually that's called BC. That's the B phase, but I have to flip the subscript around so that's CB. 20 angle 3687. I'm adding 120, just going the other way around that unit circle. So ICB is 20 angle. When you add these guys together, you're going to get 156.87 degrees amps RMS. Now, I know I'm making a lot of fuss about the subscripts and all that stuff. It's really just because it's very easy to get confused. Whenever you flip the subscripts around, you've been dealing with it on the load side, A, B, B, C, C, A, so long that you just get confused here. But to be honest with you, even if you just forgot to flip them around and just labeled them this way, it isn't the end of the world. I mean, as long as you know which one's the A phase, which is this one, which one's the B phase, which one's the C phase, you're going to be okay. But what you don't want to do is get them mixed up together so that you accidentally think this is like the B phase or something. So that's why I write it down this way, to try to keep it clear. Last thing we have to do, find the magnitude of the line voltage at the source terminals. Line voltage at the source terminals. So what that means is, when we say line voltage, we mean line to line voltage, right? Line to line voltage. So there's actually a couple of ways to do this. There's a couple of ways to do this. You actually already know what AB is. You actually know what AB prime is. You know what this is right here. You also know that this current flowing through here, you just found it. It's written on the board over there. So we know what this current is. We know what this guy is, the 600. This is this voltage source. We know what voltage drop is across this. So we could use Kirchhoff voltage loop and just find VAB. That's what we're asked to find. It's the line voltage. That means line to line. These are line to line here at the source. That's perfectly valid. Another way to do it is to look over here in the single phase equivalent circuit and do the same thing we did a second ago. We know the current circulating around. We already calculated what that is. So because of that, we can find VAN. We can find the line to neutral voltage at the source. Even though this neutral terminal isn't really real, but we can use it as if it's real because it's an equivalency, right? So we can find out what this voltage is right here. And then once we have this line to neutral voltage, we can shift it using the voltage formula to find VAB. Ultimately, we want to find VAB. I mean, the problem could have said, find VAB at the source, but they don't tell you that. They say the magnitude of the line voltage. You have to know that that means VAB at the source. Let's go and do the problem this way, and then we'll examine what would have happened if we had done it the other way, and you're going to realize that the math is exactly the same in both cases, even though you're thinking about it slightly differently. So what we want to do first is find VAN, the voltage drop between VAN. How do we do that? Well, we want to find what this voltage drop is. This source is in the same direction as if this voltage drop were here. So this voltage drop, VAN, starting at A coming to N, is going to be this. But then you have a voltage drop coming through here, so you're going to be minusing or subtracting the voltage drop across this to give you this. Another way of thinking about it is you could do a Kirchhoff voltage loop. You could say this is a rise, so you count it as negative. This is a drop. You go here to this terminal, back down as this is another voltage drop. Let's write the math down, and you'll see how easy it is to figure that out. What we're saying is, let me just write it down for a second. VAN, that's what we're trying to find, the line to neutral voltage, is going to be equal to 346.41 angle 30 degrees minus that current that we just found, that line current times that source impedance, 0.006 plus J 0.054. Before we go any farther, I want to make sure you understand this is how you find VAN, the voltage drop here, because if you don't understand this, then the rest of the problem isn't going to make any sense. Basically, what you have to do is you know what this source is, and you know what this current is, so you know what this voltage drop is across this, so of course you can find what this voltage is. And probably the easiest way to figure that out would be to say, treat it like a Kirchhoff voltage loop. What you have is, if you start at this guy and you go through a voltage rise, you treat this as negative, okay? So we didn't treat it as negative there. you'll see how everything's negated in just a second. But treat this as a negative because it's a voltage rise. Then this guy would be a voltage drop because the current's going this way, it's a drop. So this would be a voltage rise, this would be a voltage drop, right? And then when you get here, this would be a voltage drop, so you would treat that as positive. So keep this in your mind here for a second. If you were doing it as a KVL, you would have negative in front of this, positive in front of this, positive in front of this. So if you move this over to the other side, it would be negative in front of that. Move this over to the other side, it'd be positive in front of that, which is what I just said, and then it'd be positive in front of this guy here. So you'd have a negative sign here, you'd have a positive here, and then because you're dropping down again, you treat that as a positive here. So all I've done is write it in one line with the equal sign. But if you take these two terms and drag them to the other side, you have a negative here, and a positive here. So you just write your KVL loop like you always do using the same sign convention, and I just move this one variable to the other side because this is what I'm trying to find, VAN. Now what I'm going to do is I'm going to take and I'm going to plug in the value of IAA. The IAA, which is the line current, which is 3464, 66.87 phase. So this guy is actually 34.64 phase angle, 66.87. All right, so instead of writing this all over again, just stick this number in here, multiply and subtract it from this. Apologize, I got a little ahead of myself here. And so what you're going to find is VAN, when you do that math, let me just double check I'm got everything together here, is going to be, let's see, double check, yes, you're going to get 347.37 at an angle 29.73 degrees. This is not the line-to-line voltage, this is the line-to-neutral voltage, the voltage from here to here. But anytime the phase voltage and the line voltage is different, we can just transform it using the voltage transformation rule. Right, so we know how to do that. So we're going to do the exact same thing over here. So what you know is the line voltage is equal to the square root of 3 times the phase voltage. And then you shift by either plus or minus 30, but since it's a negative phase sequence, we choose the bottom sign, so we'll be actually shifting by negative 30. So the line voltage, that's what I'm trying to find, the line-to-line voltage, right, which is going to be VAB, is equal to the square root of 3 times the phase voltage. This is the phase voltage as if that were a Y source. So then it would be 347.37 angle 29.73. And then you shift by negative 30. But then you look at this and you realize, I don't actually care about the phase, I'm just trying to find the magnitude. So I wrote it all down in terms of the full-blown phase sequence just because I like to do that, but really, all you really have to do is say square root of 3 times this. I don't really even need to touch the phase. So the magnitude of VAB, which is what was asked for, is just this times this. Forget about the phase information, I don't need it anymore. Is going to be 601.66 volts. This is the final answer to the problem. Because the problem said, what is the magnitude of the phase voltage, or the phase, the line voltage at the source? So real quick recap, big problem. Put it on in a triangle where you have the source impedances, you write your currents down here in the triangle, and we talked a lot about how we know that this is 600 at an angle of 0 because it was a no-load measurement. And then we draw our single-phase equivalent circuit. In order to do that, we have to take the impedances, divide by 3 to get an equivalency. We take the source voltage, divide by square root of 3, and shift appropriately to get an equivalency of the source voltage. Then we write that equivalent source voltage here, equivalent Y impedance here. Then we do the line impedance, and the load is already as a Y, so we write it straight in our single-phase equivalent circuit. Then we can use the single-phase equivalent to find the line current AA. After we find the line current AA, we find the voltage drop VAN. The reason we do that is because once we have this phase voltage, we can shift to a line voltage by using our voltage shift rule we've been doing all along. And so we found the magnitude of the line voltage at the load. That was part B. Part C was to find all 3 line currents. We already had one of them. So we drew our little diagram and we add and subtract 120 degrees to get the other 2 line currents. And then for the next part, we wanted to find what are the 3 phase currents in the source. In other words, what are these 3 currents here? So since we knew the line current for the A phase, we just did a current shift to get the phase current here in the A phase. And so what we did is we said, well, the line current is the square root of 3 times the phase current with a phase shift. And so we just we solved for this guy, and so we plugged in the line current that we had, and we found the associated phase current, which was this guy. Then we just added and subtracted 120 degrees again to get the other two phase currents and the other two legs of the triangle by adding and subtracting 120 degrees. And then the last part of the problem, we're trying to find the magnitude of the line voltage, magnitude of the line-to-line voltage here, like VAB. I'm sorry, over at the source side, VAB over here. So the way we did it here is, since we know the current, we calculated, well, we wrote a KVL to figure out what VAN is, and it was going to basically be equal to this voltage minus this voltage drop. Okay, so this voltage drop was current times impedance, so there we go. We have the source minus current times impedance. We found VAN, and then we did another shift. Because this was a line to neutral voltage, we converted to a line-to-line voltage by the exact same thing that we always do with the voltage shifting. The line voltage is the square root of 3 times phase voltage with a phase shift, and then we found the answer to that guy. Now there's one final thing I want to actually point out in this problem here, is that we did this last part of the problem in a certain way. We wanted to find VAB, so the strategy was exactly as we just outlined. We find VAN, and then we shift it. Perfectly fine to do. But I also hinted that you had enough information to do it a completely different way. You know this current here in this triangle. You know what this voltage source here is. It's 600 at an angle of 0. The third part of the problem is asking you to find VAB. That is exactly the definition of the line voltage at the source. This is a line-to-line voltage. It's the voltage across this leg of the triangle. So how would you do that? If you wanted to find VAB here, this voltage source is exactly in the same polarity orientation as VAB. So if you wanted to find VAB, it would be 600 angle 0, that's this voltage, but then you have a current going this way opposite, so the voltage drop is plus minus. So if you want to find this voltage drop, it's going to be this one minus this drop, because this one's in the opposite direction. So I encourage you to grab a calculator, go look at this phase current here, BA. We already calculated what it is. Where's it at? BA, right here. 20 at an angle of 36.87. So go get that, go in your calculator, put 600 angle 0 in as a phasor, and then you put this current in that we just pointed to on the board because we found out what it is, multiply that by this impedance, and you subtract these guys, take 600 minus this drop, IR drop, and you're going to get a value of VAB that's going to exactly agree with what we got over here, right? That's what's going to happen. It's not black magic, it's just that I don't want to get into all the details behind it, but basically when we write the single phase equivalent circuit, we've already done a transformation of the source triangle shifting by 30 degrees and such. So when we go and we get those currents in the other domain, I don't want to go and show you a lengthy proof, but obviously it's got to be self-consistent, right? So if we know the current through the one leg of the triangle, and we know what the internal voltage source is on that triangle, then we can find the line-to-line voltage over there as well as doing it this way. I encourage you, grab a calculator and go prove to yourself that it's true. So make sure you understand this. We've now done YY circuits. We've done a lot of talking about delta sources, and we've done delta Y loads. So at this point we have done YY sources. We have done Y delta circuits, I should say YY circuits. We've done Y delta circuits. Now we've done delta Y circuits, and the only thing left to do is delta delta. So you see, there's not much more to talk about here. We're just going to have to put the last piece of the puzzle in place and see how you handle it when you have a delta source and a delta load, which is what we're going to do in the very next section.